So good afternoon. Today we are going to discuss about the electric flux density due to a point charge. Already we have discussed about electric flux density, electric flux and electric flux density, right? So what is electric flux? What is electric flux? Anybody have to respond? What is electric flux? The electric flux is numerically equal to the electric charge. Okay, the direction of electric lines of force, it is called the electric flux. Basically, the electric flux represents the direction of electric lines of force. Direction of electric lines of force. It is called the electric flux. Okay, always the electric flux lines should start at the positive charge, ends at the negative charge. Okay, and coming to electric flux density. Flux density nothing but the electric flux passing through unit surface area. It is called the electric flux density. Here, the direction of electric lines, flux lines are the horizontal. Just we have to assume, and differential surface area in the vertical. So the angle between electric flux lines and the differential surface area, that is the 90 degrees. So it is called the normal. The direction of electric flux lines normal to the surface area. The direction of electric flux lines normal to the surface area, that is differential surface area. And in the scalar form, D is equal to psi by S. Psi is the electric flux, S is the surface area. So we have to consider the d psi is the electric flux, differential electric flux, and ds bar is the differential surface area. So d bar is equal to d psi by ds bar into an bar. An bar is the unit vector normal to the surface area. Unit vector normal to the surface area. Unit vector represents the direction of electric flux lines. Direction of electric flux lines, that is the direction unit vector represents. Okay, and ds is the differential surface area. So the direction of electric flux lines and the differential surface area, this is the normal to each other. Both are normal. Normal means angle 90 degrees, or it is called the perpendicular. Okay, and next one, electric flux density due to a point charge. Electric flux density due to a point charge. Here we have to show that d bar is equal to q by 4 pi r square. D bar is equal to q by 4 pi r square into ar bar. 4 pi r square into ar bar. This is one. This is what we have to show, that d bar is the electric flux density, q is the electric charge, 4 pi is the constant, r square is the radial distance or radius of the sphere, radius of the circle or radius of the area, that sphere, and ar bar is the unit vector in the radial direction that represents the direction of a radius, that is the radial direction. Okay, and here electric flux density due to a point charge. Already we have to find the basic formula, that is d bar is equal to d psi by ds bar into an bar. D bar is equal to d psi by ds bar into an bar. Okay, so electric flux density due to point charge. Let us consider a sphere of radius r. This is the sphere. Let us consider a sphere of radius r, and point charge plus q placed at the center of the sphere. Point charge plus q placed at the center of the sphere. Please made the mute. Oh shit. Now it is audible. Now it is audible. Okay, ma. So electric flux density. ఎక్కడి నుంచి అర్థం కాలేదమ్మా మీకు వాయిస్? ఫ్రమ్ విచ్ ఆన్వర్డ్స్? ఫ్రమ్ స్టార్టింగ్ ఆన్వర్డ్స్ ఆర్ దిస్ టాపిక్ ఆన్వర్డ్స్? From where?
Electric flux due to point charge, sir.
Okay, ma. You had about electric flux density, ma? Electric
Yes,
flux
sir.
density. Okay.
Yes, sir.
Electric flux density due to a point charge. So let us consider a sphere of radius r, and an bar is the direction of flux normal to the surface area. An bar nothing but, suppose I can draw the here, this is the sphere. Let us assume this is the sphere, and we can place the point charge q. This is the point charge. Whenever the point charge q placed at the center of the sphere or origin of the sphere, then the electric flux lines originating from this point charge, originating nothing but starting. The electric flux lines originating from the point charge, then those electric flux lines are the outward flux. Outward flux. Those lines are the outward flux. And also we have to place this radius. Consider radius is the r. For sphere or circle, at any point, sorry, from the center of the point, the radius is the same. The radius may be the same. Okay, from center point, the radius, it is the same. From this one to this one, same. From this one to this one, same. This one to this one, same. Okay, from center point or center of the sphere, the radius is the same. So for all the flux directions, the radius is the r. We have to assume the radius is the r, and the center point is the plus q, that is the point charge. Then this radial direction vector is the ar bar. Radial direction vector is the an bar. I can place, here is the surface area, differential surface area ds. Then this differential surface area ds is the vertical nature, and the electric flux lines passing through the differential surface area. So direction of the electric flux lines is the this direction. The direction of electric flux lines is the normal to differential surface area ds. The direction of the electric flux lines normal to the differential surface area. Normal means perpendicular. It makes the angle of 90 degrees angle. Okay, so in this figure, ar bar is equal to an bar. Why? Because ar bar is the unit vector, that is the direction of the radial distance. Direction of the radial distance. And an direction of flux normal to the surface area. So this is also of the radius. Whatever the direction we have chosen for an bar, whatever the direction we have chosen for the an bar, that direction is also marked as radial direction ar bar. That's why ar bar is equal to an bar. Ar bar is the radial direction, an bar is the direction of flux normal to the surface area. This is about the electric flux density due to point charge. And let us consider the electric flux density is, see the previous formula. So take this previous formula, d bar is equal to d psi by ds bar into an bar, coulombs per meter square. D psi is the differential flux, ds bar is the differential surface area, an bar is the direction of flux normal to the surface area, or unit vector normal to the surface area. Normal to the surface area means what it is? Flux direction and surface area, both are perpendicular. Then take the formula, d bar is equal to d psi by ds bar into an bar. D bar is equal to d psi by ds bar into an bar. Okay. Coulombs per meter square. This is assumed as equation 1. This can be assumed as the equation 1. So it can also written as d bar is equal to, what is the d psi? What is the basic meaning of this psi? Psi nothing but electric flux. So d psi nothing but total flux. So in the form of d psi nothing but total flux, ds bar nothing but surface area of the sphere. So total flux divided by surface area of the sphere, that is called the flux density. The flux per surface area or accelerated surface area, it is called the d bar, electric flux density. And also it can be written as the d bar is equal to total flux can be assumed as the psi. Total flux can be assumed as the psi. And surface area of the sphere, generally the area of the circle is pi r square. Area of the pi r square. Surface area of the circle sphere, area of the sphere is 4 pi r square is equal to psi by 4 pi r square into a n bar. Psi by 4 pi r square into a n. Electric flux. So in the electric flux, what it is? Electric flux is numerically equal to the charge. I can show here. Electric flux is numerically equal to the charge. See this equation. Electric flux psi is equal to Q. So replace that psi electric flux value with the Q. Replace that electric flux value with the Q. That is d bar is equal to Q by 4 pi r square into a n bar. D bar is equal to Q by n, either r or is. Why? Because this r is representing the radial distance or radius of the sphere. So in radial direction and normal direction, both are same. Assume here this is also a radius of, this is also a radius of the sphere. This is also radius of the sphere. This is also radius of the sphere. Like that, we can consider the different flux directions. So each and every flux direction represent the each and every radial direction, right? Each and every flux direction represent the each and every radial direction. That is a radius direction. So this is the flux direction, and this itself is the radial direction. That's why an bar is equal to ar bar. Into an bar. This is the final equation. And also, if an bar is equal to ar bar, why? Because an bar is the direction of flux perpendicular to the surface area or normal to the surface area. That flux direction is same as the radial direction. Why? Because we are considering here is the sphere. So for sphere, each and every radial direction is equal to the each and every flux direction. That's why an bar is equal to ar bar. So if we have to consider an bar is equal to ar bar, then we get the d bar is equal to q by 4 pi r square into ar bar. Understand? D bar is equal to q by 4 pi r square into ar bar. Okay. So this is called the electric flux density due to a point charge. This formula is the this d bar is equal to d psi by ds bar into a n bar. This is the basic formula of the electric flux density, and this formula for the electric flux density due to a point charge. Due to a point charge. Suppose I can take line charge. Suppose I can take line charge instead of point charge. How can we write electric flux density? Or how can we compute electric flux density? How can we measure? Anybody have to say how to measure? Instead of point charge, I can take line charge. What it gets, d bar is equal to, for line charge, q is equal to integral L rho L into dl. Am I right? Rho L into dl divided by 4 pi r square into AR bar. 4 pi r square into AR bar. Yes or no? Please respond here. D bar is equal to, just replace Q value with the particular type of charge. Okay, for line charge, integral L rho L dl. For surface charge, integral S rho S ds. For volume charge, integral V rho V dV. Like that, we can write the electric flux density due to a line charge, surface charge, volume charge. Okay, line charge, surface charge, volume charge. Any doubts regarding this electric flux density due to a point charge? Any more doubts? Electric flux density due to point charge. Yes or no? So this is d bar is equal to q by 4 pi r square into AR bar. Actually, already we have derived the electric field intensity due to point charge, right? That is E bar is equal to q by pi epsilon naught r square or epsilon r square, right? Epsilon r square into AR bar, right? For material or medium, take epsilon. For free space, take epsilon naught. Why? Because for free space, epsilon is equal to epsilon naught into epsilon r. Okay, for free space, epsilon r is equal to 1. Epsilon r is equal to 1 for free space. That's why epsilon is equal to epsilon naught we are writing. Okay, so this is the d bar value. This is the d bar value. Already we had derived the electric field intensity due to point charge. Why? Because based on the Coulomb's force, we can derive the electric field intensity from the point charges. So now we can derive the here. Already we have derived the electric flux density to point charge. Electric flux density and field intensity. Okay, means d bar. Electric flux density means d bar. Electric field intensity means E bar. Okay, d bar units are the coulombs per meter square. E bar units are the newtons per coulombs. Newtons per coulombs are volts per meters. Volts per meters or newtons per coulombs. D bar is the coulombs per meter square. Okay, then we want to find the relationship between electric flux density and field intensity. Electric flux density is the d bar. D bar is equal to epsilon naught into E bar or epsilon E bar, whatever it may be, based on the medium. If the medium is material, then take epsilon. If the medium is free space, then take epsilon naught. That is the difference. Okay. Don't confuse and don't bother about that. D bar is equal to epsilon naught into E bar, or simply for material, D bar is equal to epsilon E bar. Whereas this same relation in the magnetic materials or magnetostatics, we want to show that B bar is equal to mu into H bar. B bar is equal to mu H bar. For electric fields or electrostatics, D bar is equal to epsilon E bar. For magnetostatics, B bar is equal to mu H bar. This is the difference between electrostatics and magnetostatics. Okay. So first of all, we know that electric field intensity is, what is electric field intensity? E bar is equal to Q by 4 pi epsilon naught into R square AR bar ma. Either small r or capital R, whatever it is. All those are the distance or radial distance. Okay. Electric field intensity formula is E bar is equal to Q by 4 pi epsilon naught R square into AR bar. That is equation 1 or equation A. Next, electric flux density. In the earlier, we had to discuss the electric flux density. That is D bar is equal to Q by 4 pi R square into AR bar. So take the equation as it is. D bar is equal to Q by 4 pi R square into AR bar. That is the equation B or equation 2, whatever it is. Then dividing equation 2 by equation 1. Dividing equation B by equation A. We get B by A. That implies left side is the D bar divided by left side is the E bar. D bar by E bar is equal to Q by 4 pi R square. D bar value is the Q by 4 pi R square. Q by 4 pi R square into AR bar. That is the D bar value divided by E bar value is the Q by 4 pi epsilon naught into R square. Epsilon naught into R square into AR bar, right? AR bar. So this AR bar gets cancelled. Q value gets cancelled. Okay. Q value cancel, and Q value cancel. R square cancel. 4 pi cancel. Finally, what is the remaining parameter or remaining term? What is the remaining term? What is ma? What it? Except epsilon naught, all the terms cancelled. Except epsilon naught. For free space, take epsilon naught. For medium, take epsilon. Okay. Except epsilon naught, all those parameters are cancelled. So we get 1 by. For numerator, the value is 1. 1 by epsilon naught. For numerator, 1 by 1 there. 1 by 1 means 1 ma. For denominator, 1 by epsilon naught there. So for numerator, 1 by 1 means 1 divided by denominator 1 by epsilon naught. So this can be written as the 1 by epsilon naught. That is equivalent to the epsilon naught. 1 by epsilon naught. That is equivalent to the epsilon naught. Okay. So we get the D bar by E bar is equal to epsilon naught. D bar by E bar is equal to epsilon naught. Take the cross multiplication. We get the D bar is equal to epsilon naught into E bar, or D bar is equal to epsilon E bar. Okay. D bar is equal to epsilon E bar. This is about the relation between electric flux density and the electric field intensity. So please remember that equation. D bar is equal to epsilon E bar. In most of the problems, it will be useful. Why? Because by using the d bar is equal to epsilon e bar, everywhere we are using for solving the derivations or solving the problems. Okay, simplifying the derivations or solving the problems, we are using the d bar is equal to epsilon e bar formula. So never forget. Okay, don't forget the relation between d bar and e bar, that is epsilon into e bar. So this is about the electric flux density, electric flux density due to point charge, relation between d bar and e bar. Okay, next one is the Gauss law. What is the limitation of Coulomb's law? What is the limitation of Coulomb's law? Coulomb's law limitation is it does not applicable for arbitrary charged bodies or arbitrary surfaces. Arbitrary charged bodies or arbitrary surfaces. Okay, arbitrary charged bodies or arbitrary surfaces. Gauss law. Gauss law is the used for overcome the limitation of Coulomb's law. Gauss law can be applicable for arbitrary bodies also, arbitrary charged bodies also. And also the Gauss law can be applicable for only symmetric charged bodies. That is symmetric, nothing but Gaussian surfaces. Gauss law cannot be applicable for non-Gaussian surfaces. Whatever the drawback in the Coulomb's law, that drawback can be overcome in the Gauss law. Also, Gauss law having the limitation. That limitation is the Gauss law cannot be applicable for non-Gaussian surfaces. Gauss law can be applicable for only Gaussian surfaces. Gauss law can be applicable for only Gaussian surfaces. Okay. So in next class, we will discuss about the Gauss law and Gauss law in integral form and Gauss law in differential form. Both the forms there. So the Maxwell's first equation derived from the Gauss law. Maxwell's first equation derived from the Gauss law. Okay.